Let us now discuss the full adder. So full adder is also a combinational logic circuit that performs addition of 3 bits. So on the block diagram, we have the inputs X, Y, Z, and then the output again, we have the carry and then the sum. So then again, we're going now to have the truth table. Okay. So we have the inputs X, Y, and Z, and then the output is designated by C and S. Again, we have three inputs rather. Okay, so we have 3 inputs. So if you have a binary with 3 inputs, so that would be equal to 8. So meaning to say, we're going to have 8 possible inputs. Okay, so that would be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Again, recall, this is actually 0 to 7. Why is 5, 1, or 1? Remember the place value. This is 2 to the 0, 2 to the 1, 2 squared, or simply that is your 1, 2, and 4. That is why this is 5, because 1 plus 4 is 5. Again, this is 3. So 1 plus 2 is equal to 3. Again, let's get the output. So 0 plus 0 plus 0, of course that is 0 with no carry. 0 plus 0 is 0, plus 1 is 1 with no carry. 0 plus 1 is 1, plus 0 is 1 with no carry. 0 plus 1 is 1, plus 1 is 10, or 0 with a carry of 1. 1 plus 0 is 1, plus 0 is 1. 1 plus 0 is 1, plus 1 is 10, or 0 with a carry of 1. 1 plus 1 is 10, plus 0 is 0, or 0 with a carry of 1. 1 plus 1, okay, so 1 plus 1 is 0 with a carry of 1. So bring down 1. Plus 1, so 1, bring down 1. So with the sum of 1 with a carry of 1. So that completes now the truth table for a full adder. Then next, to design, we have to get first the minterm using the Carnot map. So we divide this into groups of 4. 1, 2, 3, 4. So I'll write a dividing line. So again, we're going to have a K map with 8 boxes. Okay. So this would be X, Y, Z. So this will be labeled as 0, 1. So we have here 0, 0, 0, 1. Take note 1, 0 is written in here, and then 1, 1. So again, so I'm going to plot now the values for C. We have here 0, 0, 0, 1. So since I wrote X here, so that will be written sideward. So 0, 0, 0, 1, 0, 1. Then 0, 1, 1, 1. 0, 1, 1, 1. Okay. The next is the S. So let's get the minterm later on. Okay. So for the S, we have here X again, Y, Z, 0, 1, 0, 0, 0, 1, 1, 0 in here, then go back 1, 1. So 0, 1, 1, 0, 0, 1, 1, 0. 1001. 1001. Okay, so let's get now the equivalent minterm. So this one, we have here, we're going to group it this way. Then, we're going to have it this way. And then, we have here green. Okay, so let's get now the equivalent minterm. So we have here the C SOP, sum of product, meaning to say you're going to group all the ones and get the minterm. So for the red group, I have here two groups of one, or in by pair. So X, it occupies two rows, so 0, 1 for the red, so that's cancel. 1, 1, we have Y and Z. Plus, for the violet, we have, it occupies only one row, so therefore that is X. For YZ, it occupies two columns. We have 0, 1 and 1, 1. So 0, 1 cancel. Take note, this is YZ, YZ. So we compare both Y's and Z. So for Y, 0, 1 cancel. 1, 1, that is Z. So that would be X, Z. The next, we have the green group. So again, this is 1, so therefore that is X. For the YZ value, we have two columns. It occupies two columns. We have 1, 1 and 1, 0. So this is YZ, YZ. So you compare both Y, so 1, 1 in there. So that would be Y. 1, 0 would be cancel. Okay? So for SSOP, so we're going to group it by 1. Okay? So we have it this way. 1. Then we have here another group. We have here another group. Only by 1, we cannot group it by 2s or any other bigger group. Okay. Okay. So let's now get the minterm. For red, we have 0 and we're getting the SOP or the minterm. Take note, in minterm, the normal value is 1. So 1, what is being grouped is 1 and we got 0 here, so that's opposite. So therefore, that is not X. So for columns YZ, we have 0, 1, so therefore that is not Y, and we have Z. Okay, plus we have the green group. So again 0, so therefore that is not X. YZ 1, therefore that's Y. Okay, and then 0, that would be not Z. Okay, the next is violet. So we have 1 there, so both are 1, so therefore that's normal, that's X. Both are 0, that is opposite of 1, so therefore that is not Y and not Z. Then for the brown group, we have 1 there, so therefore that is X. 1, 1, so both are 1, so X, normal. 1, 1, therefore that is Y, Z. Okay, so we can now design the circuit. So how are you going to design it? You can have it this way. Okay, so we have here y, and z, you can have it this way. Okay. Okay. So therefore, this one is x, not x, y, not y, z, not z. So in here, all are AND gates separated by an OR gate. So we have here AND gate. We have yz. So this is your z. And this is your y. And then we have xz. So we have here z. We have here x. Then another AND gate. We have xy. We have here y. And we have here the x. Again, separated by an OR gate. Okay. So this is now your C. And then next is for S. So we have not X, not Y, Z. So we have here Z. Not X, not Y. So we have here not Y. And we have here not X. Okay. Then another AND gate. Not X, not X, Y, and not Z. So this is your not Z, Y, and we have not X. Okay. Then next, another AND gate. X, not Y, not Z. So we have here not Z, not Y, and X. Then we have another AND gate. We have X, Y, Z. So this is your Z. You have the Y, and you have the X. Okay. So we have one OR gate. So we'll just connect those. Okay. So this is now your S. So this is your full adder. Okay. Now what if we're going to connect the full adder using two half adders? Okay. So how are we going to do that? So take note, in a half adder, okay, so we have here the half adder. Okay, so half adders, so we're going to design it using two half adders. We have the X and Y. Okay. Okay. So how are we going now to design it? So let's start off with, take note, this is your S and this is your C. So meaning to say this is our S and this is our C. Okay? So where S, that is equivalent to X, x or y, and for C, we have xy. Okay? So, how are we going to do that? Now, let's have the S. For the S, we're going to derive the XOR implementation of this S here. So how are we going to do that? We apply the Boolean laws and theorems. So you would notice these two has a common factor which is not X. In here, the common factor is X. So let's factor out not X. So not X, not YZ divided by not X is not YZ plus not XY, not Z. We have Y and not Z plus here the common factor is X. So we factor it out. This term divided by this term, that would be X not Y and not Z divided by X. So you cancel X. So that would be not Y and not Z. Okay. Plus XYZ divided by X is YZ. Then next, you would notice this is an XOR gate, or can be rewritten as XOR gate. So therefore, this is Y XOR Z. Plus, you have here X. Now this one is an XNOR, so therefore, I can rewrite it as Y XNOR Z. Okay? So if I let this as A, okay, you would notice both are same except this one has an inverter. So therefore, if this is my A, I could also write this as A, but this time with inverter. Okay? So I could rewrite this again as not XA plus X not A. Again, this is in a form of an XOR gate. So therefore, I could rewrite it as X XOR A. Okay? So, what is this A? A is actually your Y XOR Z. That is your Y XOR Z. Okay? So, you would notice we now derive the XOR equivalent of this expression. So let us connect it now. You would notice your S here is X XOR Y. So this expression. So I could connect it here. Okay. And then with, I'm going to add Z. So this is now my S. Okay. Now how about this C? For C, I have here XY. My XY is this green group. So in order for it to arrive with this format, since you would notice this is YZ plus XZ, we cannot design it using to have ADDER. So instead, let us redesign this one or regroup the ones for us to be able to get this type of connection. So how are we going to do that? So we retain the XY since we have already XY in here. So this is the green group. So we have two ones left here which will be ungrouped. So instead of grouping it by 2s, let us try grouping it by 1. Okay? So violet, instead of by 2s, we group it by 1. So therefore, we're going to have it as, again, retain the green, which is your XY. Okay, plus we have the violet. So instead of by pair, we now have it by 1. So we have here x, not y, and z. Okay. Plus, for the red, we have 0, 1 here as individual or a single group. So 0, we have here not x. 1, 1, we have yz. Then let's apply the laws and theorems. Okay. So we have here xy plus, you will notice the common is z. So we try factoring it out. So x not yz divided by z, that would be x not y. Plus not xyz divided by z, that would be not x and y. Again, you would notice this is in a form of an XOR gate. So I could rewrite it as xy plus z. Okay. Now this one is an XOR gate. So I could rewrite it as x XOR y. Okay. Now, so let's try connecting this one. Okay. So we have here z, x XOR y. So we have here AND gate. So we have here AND gate. This is our x XOR y. So let's connect it in here. And then we have z. So your z, we have here connected in here. And then x XOR y. Okay. And okay. So this is x XOR y and z. So these equations in here. Then we have, that is ordered in xy. So I have here xy. So maybe, so let's connect it this one. 2 and, okay, we have xy OR gate. So we have here an OR gate. Okay. So I have here xy, and then this we have here the z and x XOR y. So let's connect it with the OR gate. So you have it the c. Okay, so we have now two half others. So we have here 1 and then another 1. Okay,